going to the next question. Let S be the set of all functions f going from R to R. Consider two binary operations plus and composition on S defined as pointwise addition and composition of the functions as follows. F positive g of x is equal to f of x positive g of x, and f composition g of x is equal to f of g of x. So this is the way the function is defined. Now they are asking which of the statements are true. Which of the following statements are true? Number 1, composition is commutative. Number 2, plus and composition satisfy the left distributive law. What is that? F composition of G positive H is equal to F composition G positive F composition H. Number 3, plus and composition satisfy the right distribution law. What is that? G positive H composition F is equal to G composition F positive H composition F. Okay, so go through this question, work the solution out, and you come back. Let's see the correct choice. Okay, I hope you all have got the correct choice. So let's see what the solution for this question is. Now we are asked to check which of these statements are true. Now composition is given to be as commutative. Now you have to understand composition is rarely commutative. Okay, this is rarely commutative. So that means outrightly we can conclude that this is going to be a false statement. Okay, so I don't buy into this, so you can actually eliminate that. Okay, now let's go and check if statement number 2 is true. So we are asked to show that the left distributive law is true. So F composition of G positive H of X should give us F composition G of X positive F composition H of X. Okay, now let me consider the left hand side. F composition of G positive H of X. Now this is equal to F of G positive H of X. Now G positive H of X, F positive G of X is F of X positive G of X. So this is F of G of X positive H of X. Now this is what we have got. Okay, now the mapping, we need to be a little bit careful with this. Okay, on the right hand side you have F of G of X, right? Now this is added to F of H of X. Now the understanding here is this is equal to F of G of X plus F of H of X. Now if you were to take this as 1 and this as 2, for sure, right? For sure 1 is not equal to 2. Okay, probably I can place the parenthesis. Now you might be asking me, what? How come f of g of x positive h of x is not equal to f of g x positive f of a h of x? How is it? Now I'm going to show you that by means of an illustration. So just watch this. I'm going to flip the next page and write this. So I'm saying that f of g of x positive h of x is not equal to f of g of x positive f of h of x here. Okay, so to show that, let me just take f of x to be equal to x squared. Then f of g of x positive h of x is going to be, because in place of x I need to substitute this, so this is going to be g of x positive h of x raised to the power of 2. You expand this, you get g of x squared h of x squared plus 2 times g of x times h of x. Okay, this is my f of g of x positive h of x. Okay, now let's go and check out f of gx added with f of h of x. F of x is equal to x squared, so f of g of x is going to be g of x squared plus f of h of x is going to be h of x squared. Now you see yourself, if I were to take this as 1 and take this as 2, do you think 1 is equal to 2? Are you saying a positive b the whole squared is equal to a squared positive b squared? No, they are not. So the left distributive law fails. The meaning here is, this is false, this is false. We have to check only if this is true or false. Okay, so we have to find out if g positive h composition f is equal to g of f positive h of f, right? Okay, h of f. Now I'm going to consider the left hand side, which is g positive h composition f of x. Now this can be rewritten as g positive h of fx. Okay, by distributive law this is g of fx positive h of fx. This is what we get. Now let me move on to the g of f. G of f, consider the right hand side. This is the right hand side I am considering. So g of f added with h of f. So this is nothing but x is here, x is here. You apply the composition. It's going to be g of f of x positive h of f of x. Now you get this 2 here, you get this 1 here. You compare 1 with 2. What do you see here? G of f of x, g of f of x, h of f of x, h of f of x. So from 1 and 2 we see that, what do we see? G positive h composition f is equal to g composition f positive h composition f. Hence the right distribution law is true. So what is the meaning of this? This means this alone is true. So 3 alone is true. That is the meaning of this. So let's move on. Okay, now this is a unique question. Show that composition is commutative, or instead of saying show that, I would use is composition commutative. That means f of g, is it equal to g of f? In the previous problem, we had to encounter a situation like this, and I said outrightly, composition is highly unlikely to be commutative or to be commutative. So the probability of composition being commutative is very, very rare. So that's the reason I negated that choice. Now let me prove that f composition g is actually cannot be equal to g composition f. So let me take f of x is equal to x positive 1 and g of x is equal to x squared. So f composition g of x is nothing but f of g of x, and this is nothing but f of x squared, which in turn is nothing but x squared positive 1. So this means f composition g of x is nothing but x squared positive 1. Now you consider g composition f of x, which is nothing but g of f of x, which is nothing but g of x positive 1, which is, if I were to execute this operation over here, this is going to give me x positive 1 the whole squared, which is x squared positive 2x positive 1. So the question is x squared positive 1 equal to x squared positive 2x positive 1? Is it equal? Can you outrightly state that x squared positive 1 is equal to x squared positive 2x positive 1? No. So this means f composition g is never equal to g composition f. So hence composition is not commutative. So that is the solution for this question. Please like, share and subscribe. Thank you.